So in this lecture, we're going to build off of the stuff we learned last time, looking at glucose metabolism. Pretty lengthy lecture. We won't go into that much detail again, but we had to do it once, right? But what I want to do is look at the fate, I guess, if you will, of pyruvate in the cell under a few circumstances and under a few different cellular environments. This is a super interesting section of the book, particularly section 4.3. So what happens to pyruvate? And I guess that's a question mark, but what happens to pyruvate when the cell needs more energy and if we need more energy and we don't have oxygen? Okay, so if we don't have energy, if we need more energy and we don't have oxygen, what this means is that if we need more energy, we need more ATP, adenosine triphosphate, to kind of provide that energy couple for us to accomplish a lot of the interesting biochemical transformations. And that more ATP means more glycolysis. Okay, now if we don't have oxygen, then we're short on our oxidizing agent. NAD+, okay? So with that, we have to keep those things in mind. Now let's look at the energy balance of glycolysis really quick. This is probably something I should have covered last time. Okay, if we have glucose, not going to draw that many chair structures today or in this lecture, maybe like none other than this one. Okay, so we got glucose here. It's a lazy glucose, but it does the job. We're going to react that through glycolysis to form 2 times pyruvate, 4 times ATP, and then there's some water too, some H2O. Now, for glycolysis to work, we had to plug in 2 ATPs to make our 1,6-bisphosphate, which then underwent the retroaldol and that sort of thing. We generated, we then split the molecule in half to DHAP and GAP. DHAP go to GAP, so we have 2 GAPs, which we then took to pyruvate. Now, both of those actually generated 2 molecules of ATP each. So because we put 2 in to do the reaction, to make the bisphosphate, and we got 4 out, we say the net outcome is net plus 2 ATPs. And really, that's a big reason why we're going to do this glycolysis, why we're going to use sugar for energies to generate those 2 ATP molecules. So we need more ATP is the situation I'm telling you, okay? The glycolysis wasn't enough. We need to burn more sugar. And to do that, we need more ATP to get this kick started and ultimately continue generating ATP. Now, here's the problem. We don't have oxygen. And if we don't have oxygen, that means that we're probably not doing this in the mitochondria. And ultimately, what you need to know is we're a little short on the NAD+, which takes away the H2 molecules. I could go to that particular step, but you could check too in the book to see when we do that oxidation step. I'm almost there. We needed that. Shoot, when do we need that? Oh, the glyceraldehyde 3-phosphate, the GAP. We had to do that oxidation at that position, at that point, to make the carboxylic acid. Okay, so we're short on that for that particular step. So what we need to do is we need to rely on, we need pyruvate to make some NAD+. That's what we need to do. We're going to need pyruvate to make some NAD+, because if we can make some NAD+, the NAD+ can then do more glycolysis, which gives us more ATP. Okay, so that's the goal here. All right, so what are we going to do? Well, you know, kind of the basic thing we're going to do is that we do quite a bit is we're just going to be like, okay, we need more NAD+. What we can do is we can take the precursor to NAD+, which is this. We have this nitrogen ring with 2 double bonds on either side, and then some sort of amide here that makes the nicotinamide group. If you recall, this is NADH. Now, NADH can donate 1 hydrogen to oxidize something. We could show some curly arrows here. We push the electrons around, and now we add here. Now, where are we going to add? Well, we're going to add to the carbonyl, the ketone carbonyl of pyruvate. The carboxylate is unreactive under these conditions, but the ketone can react, and then we could couple that with H+ addition too from some sort of acid source floating around. There's enzymes for this. Okay, when we do that, everybody cheer. We've now made our NAD+. NAD+. Hooray! That means more glycolysis. That means more ATP, burn more sugars, make more energy. We can keep like doing stuff, okay? So, you know, what else gets formed here? Well, you also get this other thing called lactic acid. So there, no big deal, right? So some of you might be thinking about the sores that you get, you know, the sore muscles that you get after an intense exercise, as your body's not really that great at like doing catabolism to generate ATP. So it's borrowing from its sugar reservoirs a bit more than it should in the absence of oxygen. And the way I was taught for a while until I took biochemistry is that this is due to, you know, lactic acid buildup and that sort of thing. Because what lactic acid does is, well, it's got acid in the name, so it's donating an H+, and the buildup of H+ is causing acidosis, which is responsible for the sore muscles. Okay, so as far as I understand it, as far as what I've read in the primary literature, the acidosis is totally responsible for sore muscles, okay? But if you look at this process, we've accomplished, mission accomplished. We've done what we needed to do. We have made our NAD+ to push the reaction forward. And yes, we generated lactate. Now you notice I said lactate and not lactic acid. We didn't actually generate an H+ from this particular process. Rather, what's happening is when we're generating ATP under anaerobic conditions, that is without oxygen, we're generating ATP outside of the mitochondria, and that's a heavily H+ generating process. So we're actually generating H+, which is causing the acidosis in the sore muscles concurrently with the production of lactate. But it's not the buildup of lactic acid. Lactate formation is just to help us turn over some NADH into NAD+ that's useful. It's not the lactate that seems to be causing the acidosis. So that's a little bit of a myth. As far as I understand it, happy to be corrected. Okay, so again, it's the acidosis happening concurrently with lactate formation. It's not the buildup of lactic acid that your body has to deal with. Your body is dealing with the excess pyruvate, using that to turn over more NAD+ to give rise to ultimately more ATP outside of the mitochondria under anaerobic conditions. Okay. Enough of that. We've got some lactic acid. What's another fun molecule we could make? We could do something similar in yeast without oxygen. They need energy too. They don't have oxygen. They've got to get creative. And the way they do it is through some fermentation processes that people seem to really love. And so that is the biosynthesis of ethanol. In yeast, from pyruvic acid. Okay, so we're going to take pyruvic acid here, and we're going to say, need more NAD+. The yeast says, and I don't know how to draw a yeast. Let's do this. I need more NAD+. So we feed it some sugar, and it converts all that sugar into pyruvate. And then what it does is it takes it through a very interesting process where it couples it with a TPP enzyme, and it loses CO2 to generate acetaldehyde. Now, acetaldehyde is our hangover aldehyde. So these yeast are not feeling good. But what they can do with the hangover aldehyde is they can take it and reduce it with NADH to make NAD+, because that's what they need. They don't have oxygen. They need the NAD+. Okay, so what does that look like? We're going to draw the same cofactor that's a good reducing agent. So we push the electrons through to make the aromatic pyridine. And then this is like sodium borohydride reduction of acetaldehyde. It's a no-brainer. It's easy. Okay, we can couple that with, we can let that arrow add to an H+, sure, that's in some enzyme active site. Oh yeah, I need my nicotinamide. There we go. Okay. So the outcome of this is the yeast is saying hooray because it's got some NAD+. So the yeast says, whatever that yeast cell is, it says, yay. However you prefer to spell yay. That looks terrible. Okay. Yeast is just happy. I don't know how to express happiness of yeast, but I do know how to express the happiness in the humans. That's just a smiley face. And why are the humans so happy? Well, we've taken acetaldehyde and converted it into ethanol production. Ethanol. So there we go. Ethanol from yeast, by breaking down sugars to pyruvate in the absence of oxygen, then requires the yeast to make a difficult decision, and they're going to have to go and deal with and go ahead and kind of convert the pyruvate into acetaldehyde, which they can then reduce into ethanol. We'll take the ethanol, they'll take the NAD+, consume more sugar to make more energy by way of pyruvate production. Okay, the NAD+ continues onward. So what's this TPP mechanism? Hopefully this isn't the last time we see these types of things. So TPP is thiamine diphosphate. Thiamine diphosphate, and it is a heterocyclic carbene. It's an N-heterocyclic carbene, which we've talked about before. We have a plus on nitrogen, negative on the carbon next door, and if we dump these electrons in here, we get a really awkward structure that's just a carbene. And so we do what I called Rovis chemistry. It's just kind of that's the chemist that worked on this. Anyway, what this can do is we can add this to our pyruvic acid. Okay, I'm going to draw that as the pyruvate. That's better. That's better biochemistry. The negative charge is going to add to, and I'm going to emphasize this is carbene-like. Okay, we're going to add to the ketone carbonyl to give still an aromatic species. We're going to get this thing. which we'll just let that engage with an H+. Thiamin's always adducted in an enzyme active site, so that H+ is on there pretty quick. It's probably not much of a separate step. Okay, now I'm going to draw this a little bit more carefully. Okay. Now the CO2 recognizes an opportunity to neutralize itself, where it can take the negative charge to make a carbon-oxygen double bond. That's going to sever this carbon bond to make that carbon-carbon bond to make a carbon-carbon double bond into the heterocycle and push electrons into the nitrogen atom, which gives now a neutral nitrogen species here. Okay. Now this species isn't going to last too long because we can react with an acid where the nitrogen comes over and an H+ gets added to what was the carbonyl carbon of our ketone. So now the nitrogen's back as a positive charge, but at least it's aromatic now. Okay, now it's at this point that what we can do is let some sort of base come in, pick off the hydrogen on the OH, push down to make a carbon-oxygen double bond, and then we're going to swing these electrons over to the atom, and that's going to regenerate our TPP while simultaneously making our acetaldehyde, which was the goal the whole time. So the TPP is a cofactor, but it's a catalytic cofactor, unlike the redox NADH, NAD+. Those things get oxidized and reduced, and you have to kind of do the opposite of what they just did to get them back into a useful form. Here, our TPP is catalytic, and it's built into an enzyme active site. It's like the PLP cofactor, and there's our acetaldehyde. Acetaldehyde. Okay. So the book goes through an approach to using pyruvate productively in the presence of oxygen. It doesn't actually show the involvement of oxygen, it turns out, but it can show an alternative productive way. I'm not going to go through that. I thought these were the really interesting ways, but with oxygen, with O2, what you do is you take this species that we just had, adducted to our TPP illid, and instead of making acetaldehyde, what you're going to do is take CoA SH and make acetyl CoA. Acetyl CoA. And to do that, you're going to use two cofactors. You're going to use FAD, which we talked about last time. FAD is going to make FADH2. And you also need this interesting cofactor that has a disulfide bond in it. So the FAD goes to FADH2, which then reacts with NAD, well, okay, I thought this made sense to me, but apparently you take NAD plus and then react that to make NADH2 to get back to FAD. Okay. I don't understand that catalytic cycle and how it relates to oxygen. We must have oxygen oxidizing the NADH2 or something by some pathway that the book didn't cover. I thought I had that. That's my bad. Okay, we'll stop there. You can make acetyl CoA if oxygen is present and kind of keep going that way. Okay, so oxygen not present. We're desperate for NAD+, so we need to find something to do. Some way to make NAD+, and that's where pyruvate comes in. So it must be that oxygen allows you to productively make acetyl CoA, which we know is so useful in fatty acid biosynthesis. Oxygen being present means that we can have as much NAD+ as we want. We can use that NAD+ productively to make acetyl CoA as opposed to ethanol, which that would be horrible if we were making ethanol because it would be toxic to us, or lactic acid, which generally means we're building H+ up other places and getting sore the next day. Okay, we'll end this lecture there. We'll pick up, perhaps we'll pick up. I'll decide if we're going to do another one. Okay, anyway, this is fun. I'm having fun. Okay, you guys have a great one. We'll see you later.